Hi, I'm Colin Gordon from Drexel University, and I'm going to talk today about my eCoop Perl designing with static capabilities and effects. Basically, I'm concerned with this question of what's the relationship between static capabilities and type and effect systems. Because capabilities, really the reason they exist is to restrict or reason about program effects. Generally, what we do is we set up things so that our language has the following property that uh, for a given expression or part of your program to do something, it must be explicitly given the capabilities to do it. So whether this is accessing security sensitive resources or modifying certain parts of the heap, this gives us a very nice general reasoning principle where if you don't give certain capabilities to part of your program, then you know that part of the program cannot do the things it has no capabilities for. And this because it's very outside in, it doesn't actually need to dig through the details of the internals of this program fragment. It yields what are generally considered fairly simple reasoning systems because they're not concerned with the inner guts of whatever program fragment you're looking at. They're just looking at are certain capabilities going into this, yes or no. And you can do this statically, you can do this dynamically. We're going to talk today about a particular static manifestation called reference capabilities, where the capabilities are the combination of having a reference to a particular object and the type of that object, which might say that reference is usable for doing some things but not usable for doing other things. And aliases might even have different capabilities to the same object. At the same time, we still have this alternative approach of classic type and effect systems, like what we think of for Java's checked exceptions, where both of these are really about establishing upper bounds on the behavior of some part of your program. So if they're both generally useful for this same high level purpose, why do we have both? The answer, of course, is that there are trade offs between these two kinds of systems, and if you've worked in both of these kinds of systems, you probably already know them, at least intuitively, but nobody really talks about them much. We'll talk about trade offs between this data race freedom system and that data race freedom system, but we don't talk about how many of those trade offs are due to fundamental design choices, like using capabilities versus effects versus something else, versus what come down to sort of lower level decisions about sort of what kinds of code if people basically tried to make this work for. And as a result, people who are new to these areas need to either learn directly from an expert or learn sort of by trial and error. And weirdly, there's no established language to talk about these problems, even though there's sort of recurring trade offs between these classes of systems. So let's talk. We're going to talk about a couple examples rooted in my prior work because I'm just going to pick on myself and my own shortcomings here. But I do believe that what I am going to say generalizes well beyond the stuff I've worked on. Let's look at one example to start with, one approach to constraining effects using capabilities, and let's talk about read-only references. So this is a particular, very broad class of reference capability systems, where basically some references let you read or write, just do whatever to an object, and other references let you read but don't let you modify the object. With a couple extensions, you can build this up to a system for things like data race freedom. The system I worked on a number of years ago is called M#. It was a project with Microsoft. And the ideas from there are actually basically what were cleaned up and extended and very greatly improved in the Pony system a few years later, which you can still download and use today, and people do. For our example, we're going to focus on two capabilities. There are a few more in my system and even more in Pony. But the important ones are these. They're writable references, which, like I said, are regular old read-write, as you see fit references. And at the same time, there are also readable references, which are read-only not only on the immediate object the reference points to, but if you start accessing further parts of the heap through that readable object, like reading fields out of a readable reference, then you get back only readable data. So having a readable reference is actually a constraint not just on modifications to that referent, but everything reachable from it, unless you have another writable reference to it somewhere else. So you can have readable and writable aliases to the same object at the same time. And just these two actually is already enough to give us capability-bounded reasoning about race freedom. So this is one of the concurrency rules from M#. And basically what it's saying is if we want to compose C and C prime in parallel, and they're individually both well typed, then to know if it's data race free to compose them, it's sufficient to just check that neither thread gets any writable references in its input environment. That's it, right? This is just, if there's no writes to shared data, then there can be no data races, which require simultaneous reads and writes. And this is generally considered to be a relatively clean rule because the only concurrency specific check in here is just, are either of these threads getting writable references? That's it. That's the whole check. And it's a very simple syntactic check. And it works quite well. I'm sweeping some details under the rug here, but it scales up to very large systems. But it does have some quirks. So let's look at one of these quirks. Here's a little bit of code typed in an environment with a readable reference X and two writable references Y and Z. And this code basically, it does a whole bunch of work with X. It digs around in stuff reachable from X, but in a read-only fashion, maybe computes some results. But then somewhere in the middle, we have this innocuous local variable assignment between Y and Z. This actually cannot be parallelized using the rule on the last slide because this code's input type environment has writable references. So the presence of Y and Z prevents this from being parallelized that way, even though it's really totally fine, right? Y and Z, this is just a local variable assignment. This is not going to cause a data race. But the rule basically looks and says, well, you have access to writable references, and it doesn't inspect the internals of the thread's code. So it says, well, conservatively, I'm not going to let you have those writable references. You can't run that in parallel. So what's happening is basically that rule is failing to make a distinction between having access to these writable references and actually using that access to the writable references in a way that causes data races potentially. So I propose to call this distinction that's not being made on the previous slide's rule the use-mention distinction. So this is an existing term from philosophy that comes from a wide range of arguments basically failing or having other problems basically because they conflate the essential use of a concept in a meaningful way with mere sort of mention of an entity or concept. So this is a little bit weird. Turns out effect systems don't have this problem, basically because in effect systems we tend not to raise non-trivial effects unless we actually see a meaningful use. So we can even see this in hyper-simplified examples like this one. Let's say we have an effect system with two effects. We have no heap access and we have heap access. And in that system, it's very easy to write a rule that says, well, if you have a local variable assignment that doesn't touch the heap, so its effect is no heap access. And that alone is enough to parallelize a local variable assignment regardless of the types of the variables being assigned. So what just happened? Well, basically, the seeming simplicity of the capability-based reasoning comes from conflating use and mention, right? It's sound because you can't use things that you're not even allowed to mention, but since the capability-based reasoning checks for mention, it's very imprecise. So if there are cases like this local variable assignment where you, in some sense, mention resources without actually using them, then you basically, in some sense, get false rejection of code that's actually okay. Now, strangely enough, this is a problem, but it's not fatal because these capability-based reasoning systems have been used for lots of stuff. So even just sticking to this read-only reference style reasoning, M# was used to write several millions of lines of code of operating system internals. Pony is used in the real world. Rust arguably has some flavor of this, not as directly. So what happened, right? Why can we do all this stuff with systems that work on these principles when they have such a bizarre shortcoming? Turns out the answer is a little bit surprising, or was surprising to me when I figured it out. It's that we have weakening in the type systems most of the time, right? These are the rules that say, well, I have extra information about these variables. Let me just forget about those variables completely for a minute, do a bunch of other stuff, and then bring them back after I'm done with that thing. So this means, for example, you can take that local variable assignment, move the variable assignment someplace else, maybe before you fork the threads off, then frame away those writable references, and now you're left with only things that you can safely pass to two parallel threads. So actually, this capability-based reasoning interacts in a really critical way with weakening or framing. Sadly, this only works for some problems. So here's a problem where it doesn't work, even though it looks like it might. So most GUI frameworks use a distinguished UI thread to handle all user input. So if you press a button or press a key on the keyboard, it invokes a handler on this particular UI thread, and that's the thread that is also responsible for all updates to the UI. Now, since there's only one thread doing this, then you're supposed to use background threads for anything that might take a while. This way, something slow like I/O or high compute might happen in the background, while you can still get a responsive user interface. And as soon as you adopt this architecture, basically every implementation imposes the requirement that if you actually want to update an element of the visible UI, this has to happen on the UI thread. It cannot be done from a background thread for a variety of interesting reasons we don't have time to talk about right now. And long story short, if you don't do this, depending on the language and framework, you might get exceptions, you might get crashes, you might get corruptions in the visible interface or other terrible problems. So let's think about how we can prevent this. Well, if you want to do this, one of the first things you need is some way of identifying when are you updating the UI. Well, turns out in Java, this basically is a matter of, are you calling a method on an object that represents a user interface element? That's it. So this kind of already sets us up quite naturally for a reference capability or object capability interpretation of those UI elements. Because basically, if you don't let the background threads hold references to UI objects at all, then trivially, they just can't access those objects, right? You need the reference in order to call the methods. And this is totally sound. So this prevents that problem at the cost of being totally useless for basically all existing code. So here's what existing correct code generally looks like. So let's start with this label variable on the UI thread. This is basically a text box. And we're going to fork off some stuff on the background thread, and when it's done, update the text box to say the work is done. So the first thing we do is pass that reference to the background thread, which is the thing we just said was not permitted under capability-based reasoning. So immediately, basically all code using standard Java UI libraries will not fit in that model, so we need something else. Then this background thread will do its slow computation and eventually pass that thread, that reference back to the UI thread, and then the UI thread will actually invoke methods on it and update the UI. So the code is correct with regard to this threading model, but accepting this correct code, and there is a whole lot of code that looks like this, means we have to distinguish use and mention. We have to recognize in the type system that this background thread has access to and basically mentions these UI elements, but it doesn't actually use them in any essential way. So we have to use an effect system for this problem, and that's what I ended up doing a number of years ago. And so maybe we look at this and we say, okay, well, all right, so maybe we'll just always use effects, right? Well, no, that doesn't work either. Turns out, and here we're going to speed up and gloss over a lot of details that are spelled out in more detail in the paper. If you take a system like this read-only reference approach we discussed earlier and try to convert it into an effect system, you very quickly reach two conclusions. First, to have any hope of doing this, you basically end up embedding a flow-sensitive pointer analysis into the type system. Now, this can be done. There are plenty of examples of this happening, but a flow-sensitive pointer analysis in the type system, most people would agree, is a lot more complicated than those capabilities we saw earlier. And a second follow-on effect that takes a little more thought to see, but shows up also pretty quickly, is that basically, in order to come up with usable procedure summaries or overall method effects, basically the effect system has to kind of make its own decisions about when do certain variable access modes get collapsed into the same sort of effect version of a permission. And then you throw transitivity of those read-only reference permissions into the mix, and things get even messier. So we might look at this example, which is in more detail in the paper, and we might ask, okay, well, if that's such a mess, why was the capability version comparatively so much simpler? Well, it turns out the answer is another sort of very subtle, easily overlooked aspect of the design: type contexts. Type contexts already conflate data that is handled similarly. Whereas if you try to do this in an effect system, you basically end up needing to sort of reconstruct a lot of the work that type context would naturally already do in the effects themselves. Which means then that if you're going to do something like this, adding reference capabilities to an existing type system is in some sense sort of a less invasive change. It has less friction with the existing restrictions the type system imposes compared to sort of rebuilding a lot of the same conflation and oversimplification in an effect system. It's fair to ask, okay, is it just these weird transitive read-only references that have this problem? Also no, and the paper talks about another example. So wrapping up, static capabilities and effect systems both have their place. Capabilities generally are considered to be simpler systems, but they have the cost that they can't tell the difference between using something and merely mentioning it. Effect systems are more powerful in that they can distinguish use and mention, but if you start having to talk about specific pieces of data in the effects, things can get pretty unwieldy pretty quickly. Also in the paper, not discussed, is this effects can be a useful intermediate stage, and using them to enforce global invariance is also really underappreciated. Thanks.